We're going to take a quick look at hypothesis testing for when we want to compare two variances or standard deviations to each other. We're also going to look at this in StatCrunch. If you haven't watched any of the previous videos about basics of hypothesis testing, you will need to go back and watch those before you proceed with this video. So if we are going to be comparing two variances or standard deviations, we have three requirements that we need to meet. First one is that the populations are independent from each other. The second one is that the samples are simple random samples. And the third one is that each of the populations must be normally distributed. And again, this is regardless of sample size. So we don't have the central limit theorem that we can apply here. This is a rather strict requirement, meaning if we do not have both populations normally distributed, this is not an appropriate test to do. Once we have our requirements checked off, then we can go ahead and we can work on our null hypothesis. Now we're going to be comparing two groups, so we're going to have group 1 and group 2. With this particular test, group 1 needs to be the group that has the larger sample variance, and that'll carry throughout this type of problem. So our null hypothesis is going to have a variety of different forms. If we are just comparing standard deviations, we could say that our null hypothesis is that the population standard deviation of group 1 is equal to the population standard deviation of group 2. Now, if we're doing variances, we could write it as the population variance of group 1 is equal to the population variance of group 2. Or we could write these values as a ratio to each other. So if these two values are equal, and we write them as a ratio, that means the ratio would be equal to 1. So think of if you had 10 equals 10, and then you wrote that as a ratio, 10 divided by 10 is equal to 1. So that's where this 1 comes from, and that wouldn't change. Or if we wanted to do that when we are working with variances, our ratio would still be 1. Now, our alternative hypothesis can take the three typical forms that we've talked about, where we have the not equal, the less than, or the greater than. And it could also be in any of these particular forms. So I didn't write all of them out, but if we are using just standard deviation 1 equals standard deviation 2, then we would go with the alternatives that either the standard deviations are not equal, standard deviation 1 is less than, or standard deviation 1 is greater than. Now, if we're doing variances, just make sure our notation here that we have the variances in those places. If we are writing it as ratios, we would still follow the same process. We would have our ratio is not equal to 1, and then we would have our ratio is less than 1, or our ratio is greater than 1. Same thing for our variances. If we wrote them as a ratio, we would have, it could be not equal to 1, it could be less than 1, or it could be greater than 1. Basically, you want to be consistent. So if your setup for your null hypothesis is like this first one, do your alternative hypothesis in the same format. If you set it up as a ratio, do your alternative hypothesis as a ratio also. So once we get our requirements checked off, so we know it's an appropriate test, we have our null and our alternative, that brings us to our test statistic. Now, when we are comparing two variances, we are going to be using an F distribution. Our test statistic for the F distribution is actually probably our easiest computation that we have out of all of our hypothesis tests. We take the variance of our first group divided by the variance of our second group. And keep in mind that the first group has to have the larger of the two sample variances. That is very important. We will need degrees of freedom for this. Now, on the standardized F distribution table, you are going to have numerator degrees of freedom and denominator degrees of freedom if you do this by hand. Our numerator degrees of freedom are going to be the sample size of group 1, and remember that's determined by which one has the larger of the variances. Subtract 1, that'll give you your numerator degrees of freedom, and then your denominator degrees of freedom are going to be your second sample minus 1. Once you get to that point, then you would need to choose the critical value method or the p-value method in order to perform the full hypothesis test. So here's going to be our example. A researcher wants to test the effects of a new fertilizer on the concentration of oil in the tea tree. Let's assume that the concentration in treated and untreated trees is normally distributed. The researcher takes 32 samples from untreated trees and finds the mean concentration to be 0.53 grams and a standard deviation of 0.242 grams. From 26 samples of the treated trees, the researcher finds the mean concentration to be 0.55 grams with a standard deviation of 0.186 grams. Perform a test to determine if the trees treated with the fertilizer vary less in the concentration of oil in their leaves. So the first thing I'm going to do is I'm just going to make a list of my information. So I'm going to do untreated, okay, and then I'm going to do treated. Now at this point, I haven't decided which one is group 1 and which one is group 2, but we will do that when we get to the end. So my untreated, my sample size was 32. My mean of that particular sample was 0.53. And my sample standard deviation was 0.242. Now my treated group, my sample size was 26, my mean was 0.55, and my sample standard deviation was 0.186. I'm going to go ahead and compute my variances already. So my variance for untreated, I'm going to take 0.242 and I'm going to square that value, and that's going to give me 0.058564. So that's my sample variance for the untreated. And my sample variance for the treated, same process. I'm going to take my standard deviation, 0.186, and I'm going to square it. And when I do that, I get 0.034596. Now, it told me previously that group 1 was the one with the larger sample variance. Well, if I look at my values here, my untreated has the larger sample variance. So this is going to be group number 1, and this is going to be group number 2. So I'm going to go ahead and put my subscripts now on each of those, so that way I keep them straight when I'm doing my computations later. All right, so we need to check our requirements. We're going to assume that these samples were simple random samples, and it tells us up here that they are indeed from a normal distribution. And then we're going to assume that our samples are also independent of each other. It doesn't give us anything in the problem to question otherwise, so we're going to go ahead and make those assumptions. So that leads us to writing our null and our alternative hypothesis. I'm going to go ahead and just write using the equality symbol as opposed to the ratio. So I'm going to test, is the standard deviation of my first group equal to the standard deviation of my second group? Now, my alternative hypothesis, it asked, we want to perform a test to determine if the trees treated with fertilizer vary less. Well, the ones that are treated with fertilizer, that's group 2. So we're asking, is group 2 less than group 1? Well, now typically we want to keep our notation in the same order. So if we want to find if group 2 is less than group 1, that's equivalent to saying, is group 1 larger than group 2? So I'm actually going to be using a greater than symbol here. So you have to be very careful with these because our groups are very defined by their values. Even though the word very less is in here, we end up using a greater than symbol because of the order of our groups. So we have our null hypothesis, we have our alternative hypothesis. We can go ahead and compute our test statistic. So my test statistic says I need to take my variance from group 1, 0.058564. I need to divide that by my variance from my second group. And when you do that computation, you should end up getting 1.6928 approximately. So this right here would be our test statistic. Then from there, you would have to decide if you wanted to use the p-value method or the critical value method to determine if you're going to reject or fail to reject your null hypothesis. So let's go ahead and take a look now at StatCrunch. And in StatCrunch, we're going to go to variance stats. This time we're going to go to to sample, and then again, you would select with summary or with data depending on the information you're given. All right, so we are here in StatCrunch, and we are going to go to the stat menu. We're going to come down here to variance stats, to sample, and we are going to do with summary. Now, again, notice up here for my sample one, it's asking me for my variance. It's not asking me for my standard deviation. So make sure that you type in the variance for our first group, which we had already computed, and that was the 0.058564. Our sample size for that group, that was the 32. So those were our untreated trees. And then for sample 2, again, it's asking us for our variance, not our standard deviation. So we want to type in the variance we computed, 0.034596, and our sample size for that group was 26. Now, StatCrunch writes our hypothesis in the form of a ratio, so we're going to leave that one alone. And then down here, we want to make sure that we check the appropriate box. We had, I believe, a greater than symbol there because of the way that our groups were worded. And we are going to go ahead and push compute now. We can see from our output table here, here's our F statistic, which is the same value as what we got. If they were off just a little bit, that would have been due to rounding issues. And then I also have my p-value here of 0.0904. So then I could use the p-value method pretty easily in order to determine the results of my hypothesis test. So my saying is if the p is low, the null must go. So my alpha value from the problem, I believe, was 0.05. My p-value is not lower than that, which means I am not able to reject the null hypothesis. So as of right now, we do not have sufficient evidence to say that the concentration of the oil in the leaves was different from the treated to the untreated trees.